Hello everyone, I'm Victor, and I'll be talking to you about simplifying network optimization for SDN deployment. Joint work with my advisors, Mike Ryder and V.S. Sikar. Let's talk quickly about SDN. Overview of it. I think a lot of us have become familiar with this picture. You've got your data plane, you've got your control plane, everything is great. There are a lot of SDN applications that are running on top of your controller. There could be a whole lot of them of different kinds, and you've got this nice engineer or a guy who's typing everything up and everything's great. Well, this is kind of an oversimplification, and not even because I'm ignoring all of the complicated stuff that happens between the control platform and the data plane, mostly what happens between the application and the control platform, right? What we have is not an engineer, but a scientist, much like one of us, who's got a whole bunch of toolboxes sitting next to him, right? Whether it's an optimization toolkit, it's a book of all the fancy algorithms we learned, or even their colleagues. And so it's not a trivial process to write an SDN application, especially the one that does something with optimizations. So network optimizations are very common, right? Even something as simple as MaxFlow or traffic engineering, all these classic applications we've learned. Optimizations creep up in recent literature. We've seen a lot of papers published in networking conferences we all love. And they all, at some point, try to provision the network using a network optimization. To write one of these papers is actually not an easy process either. Here's how I approximate it, and it's illustrated with various stages of anger you might experience while you go through it. Right? So you try to learn your theory and your optimization, trying to become a theory expert, much like some of you guys. Then you formulate your problem using a linear program, integer linear program, any other fancy techniques you know. You solve it with a solver, and at this point you start getting irritated. You know, this is taking up your time. It's not just, oh, I've coded up something in a week. And then you realize, oh, I'm actually solving an NP-hierarch problem, so you have to go, okay, well, how do I develop a heuristic for this? You code that up. You still have to parse what your solver gives you, and then go, okay, how do I translate that to your SDN controller? All right. So what we'd like to do in our work is our vision is take the scientist guy with all of his fancy toolboxes and replace him with an engineer, essentially, who can actually write things much quicker using some sort of simplified interface. And maybe we'll replace him with management. I don't know. That's kind of taking it a little too far. But so how do we do this, right? We'd like to introduce an optimization layer. It's a layer that runs on top of your control platform and kind of hides all this theory stuff. So all the theory and fancy stuff is sandwiched in the optimization layer, which exposes a much simpler API to the engineer who's writing the application. So what are we aiming for? We are aiming for no custom heuristics, right? You don't have to reinvent the wheel and come up with a heuristic each time you have a new problem. We would like to give the engineer the ability to specify high-level goals or high-level intents about what should happen in a network and not muck around with little variables and all the other stuff that would normally go into an optimization. We would like to be able to give developers the ability to rapidly prototype an application. And that also kind of ties in with the last point, which is an application should be something fairly quick and easy, like 20 lines of code, and you've got yourself a traffic engineering or a service chaining application that you can play with. So, OK, why hasn't this been done before? What's really the trick here? What's the challenge? Well, the challenge is achieving two properties that we as computer scientists really love, right? We love generality and we love efficiency. So what we've seen before in previous work is a lot of frameworks that cover generality really well, but they're not efficient, right? They can't generate the solution really fast. Or we've seen custom solutions, and this goes back to heuristics and all these papers you see published in networking conferences, where they solve one problem very specifically and very well, very fast, but it's not sort of reusable. The solution you've come up with isn't reusable to other problems. Now, in our work, Sol, we try to achieve both. So let me tell you how we actually do that. So SOL stands for SDN Optimization Layer. This is the sort of framework we're proposing. This is what we're designing. And it is the optimization layer that sits on top of the control platform and talks to a solver, you know, such as Cplex or Gurobi or whatever. It's a general linear program solver. It exposes a set of interfaces, or APIs as we call it, to the developer, or the SDN applications, the developer who writes these applications. The good thing about this, the optimization layer and the control platform are logically centralized. So it's a good fit for SDN, right? That's what we knew for a while now. Optimizations are great when they're centralized. The problem is this set of applications is incredibly diverse, right? So a number of things you might want to express in your application is very large. So how do we model all of them? Let's talk about that. It's the first insight we have is the path abstraction. So all of these optimization problems are recast to be path-based. And the second thing is we apply policies to your network by applying predicates to the paths. So let me talk about these in a little more details. First of all, path-based recasting. If you think about your classic networking problems, such as MaxFlow, you can write a lot of them as integer linear programs or linear programs. If you wanted to do MaxFlow, what you would see is something like on the left. You have your network, you have your source, you have your destination or sink, S and T, and you have all of these variables that talk about how much flow you're sending on each link in the network, right? Fairly similar. Now, there is an alternative way of writing that same problem that you kind of see on the right, is instead of thinking about these variables being per each link, you think of variables being per each path. Now, you have to enumerate all of the paths, and you have to assign them all of these variables. And that's kind of a problem, right? So what happens is you have a lot of these. I'll touch on that in just a little bit. Second thing I would like to say is policies as path predicates. We, as networking people, love policies, right? That's what we do. We route traffic according to a policy. Now, encoding that in an optimization is very difficult, or can be very difficult. So what we do is we separate that out. We say we generate the paths first, and then we go, OK, paths can be valid or invalid according to a predicate. So in this particular example, if you would like to say, oh, my traffic must hit a firewall and a proxy, and it must go from node 1 to node 5, you will end up enumerating your paths and saying, OK, we have 2 valid paths and 1 invalid path because it doesn't hit a proxy, an IPS, or sorry, firewall. So why do we do this? What this buys us is generality, right? So because a predicate is an arbitrary piece of code, essentially, you could make your paths to be whatever you want them to be. You could say firewall followed by proxy. You could say path is valid on Wednesdays. So that's the good thing. However, to achieve this, we do have to enumerate all of the paths and then filter them, right? That presents a problem because exponential number of paths in the network, large optimization size, long runtime, right? Bad efficiency. We've just kind of sacrificed one of our goals. We have to get back at that efficiency once we've got this much generality. How do we do it? Sold process, right? We do generate all the paths in the network first, right? So yes, there are a lot of them. We enumerate them, all simple paths, and we keep the ones that match the predicate. There's still a large set of them, so that's why this is an offline step. Right? It's the first thing we need to do before we even get to the actual optimization part. Number 2 is we do path selection or path pruning, right? This works as a general heuristic step that lets us throw away a bunch of the paths we consider not to be important in the optimization. This is the step that lets us get back some of that efficiency, right? So out of the millions of paths you could have in a network, we pick a few that we think are going to be good. Then, using those paths, we can create the optimization. So we construct these sort of linear program or ILP that we then solve. And we finally use the output of that solution to actually deploy the rules or the configurations on a network. While this step might be kind of dismissed as trivial, this is one of the things that allows us to sort of do that substitution from the scientist to engineer, right? It just says, I give you the high-level goals of the network, and you do the rest. So given all of this, let me just quickly talk about like an implementation. We've actually done this. This is implemented as a Python library. It interfaces with a Cplex solver and even honest controller. We did end up prototyping a bunch of applications just to show you that both the classic problems and the sort of problems from recent literature can be expressed in our framework. So we've taken MaxFlow and traffic engineering. We also have taken Elastic Tree and Panopticon simple as examples of work from the literature that could be expressed using our framework. Now, just to give you a flavor of what this would look like for a few systems people in the crowd, if you wanted to do something like MaxFlow, Yeah, I'm ignoring a little bit of a setup here, but in 6 lines of code, you essentially have yourself a MaxFlow formulation, right? And so what you're doing is you're saying, yes, we'd like to initialize an optimization. This is your topology and your source destination pairs. Then you give a few parameters for path generation and selection. And then you proceed to create essentially your problem. You're saying, I'd like to allocate some flow from my source nodes to my destination nodes. Then you actually create a little function that dictates how resources are being consumed in the network. In this case, this is just bandwidth. And then you proceed to say, OK, we would like to cap our links, right? Who likes overloading their links? After this, we just go global objective, which is MaxFlow, and then we solve the optimization, right? 6 lines, you've got yourself a MaxFlow problem. Now, let's say you want to do traffic engineering. It's no longer MaxFlow, it's your load balancing your links. Everything is pretty much the same except these 2 lines, right? Now you would like to route all traffic that you have. So for all your demands, you'd like to not drop anything. And you would like to minimize bandwidth load on your links. And just like that, you actually have yourself 2 applications. What used to take a lot of time now takes hopefully less. So a few quick key questions we'd like to ask before we sort of go on to the evaluation. So does it reduce the development effort, right? Are we actually making anybody's life easier? Is it faster than the original? And is it any worse than optimal? Because as I mentioned, we do have a heuristic step that kind of throws a lot of things away. Let's take a look at development effort. The short answer is yes. We believe we do reduce development effort. So we've prototyped these 3 applications from the literature. In all of these, the optimization that used to take half a page to write just mathematically can be now done in about 20 lines of code. Now, I admit that lines of code isn't the best metric in some cases, but it's a good place to start, and we do think that it's an important metric to take a look at. Second question we had is runtime. Is it any faster than the original? And the answer is yes. So here you see 2 graphs, 2 prototype applications, panopticon and simple, taken from the literature. On the x-axis, you see different topologies with their sizes in brackets. And on the y-axis, you see the time in seconds to actually solve the optimization. I'd like you to know the log scale, and I'd like you to know the shaded regions. The shaded regions mean that the original did not complete within half an hour, right? So we just decided to cut it off. We didn't think it was worth it to run it longer than that. And so the takeaway here is that the SOL implementation is actually orders of magnitude faster than the original integer linear program that was formulated in this paper. And in all of these cases, we are less than 1% from being optimal. All right, I don't have a lot of time, so let me just go straight to the potential future directions, right? There is some work left to do here, especially from the theoretical side. We would like to to analytically show why path selection is effective, right? At this point, we've said, OK, let's throw away a lot of paths and just keep some. And I didn't even tell you how we keep some. There are 2 strategies. They're very, very complicated. Shortest path and random path, right? Why does it work? There is a good intuition for it. For example, random paths work because if you want to load balance, randomness just kind of lets you load balance naturally through the network. But can we prove any sort of theoretical bounds on it? Perhaps. And the second thing is kind of flipping the problem upside down a little bit and saying, can we create path selection that honors bounds and optimality? So I'd said that we've done some path selection and we are less than % away from optimal. Can we do it the other way around, where I say, I want % away from optimal, give me the paths that I need to put into my optimization. So just a quick summary, getting SDN benefits requires a lot of expertise at this point. SOL lowers the sort of barrier of entry for developers and helps you write the applications in a much easier way. It leverages the path abstraction plus sort of this general heuristic that is path selection. It is very efficient. We can deploy a network in about 15 seconds for a basic traffic engineering application. And we do believe it creates new opportunities for future work. So if you have any questions, happy to take them or shoot me an email. Our code is public on GitHub if you'd like to see the internals. And there is a paper that appeared in NSDI 2016 if you'd like to read a little more. Thank you.
So, great work. The thing is, like, my question is, like, so this simplifies a lot of stuff, but by doing that, is it losing some flexibilities or you know, freedom of doing stuff? Because, like, for example, using your language or framework, can you say, like, okay, you want to do some waypoints, things like that? Can you do that?
Yes. Right. So generating a path using the path predicate, you can just filter out the paths that you don't like. Right. So that we can do. There's certainly things some things we can't do right now, or maybe we'll never be able to do. I don't know. I mean, right? There's limitation on generality to almost everything.
Did you get a chance to evaluate the quality of your solution?
The quality, you mean?
So how good your solution is?
Yeah, we did. So in most cases, we are less than 1% away from the actual optimal solution. Yeah. Any other questions? All right. Thank you.